Hello everyone, welcome to another video on conjugate beam method. So we'll be solving another example using this method. So the first step is to calculate the support reaction. Calculate the support reaction. We draw the free body diagram. Then from the free body diagram, we will calculate the support reactions. We will take summation of moments at A equals to 0. Negative. So this is going clockwise, going to be positive moment. Also clockwise. Then this will go negative. We have this. When you simplify all this, you arrive that RD is equals to this. Then the next step is to take the summation of forces in the vertical direction. With the convention that the ones going up positive, the one coming down negative. So the RA and RD are going in the positive direction. Then the loadings are going in the negative direction. Then we calculated the support reactions. The next step is to draw the M/I diagram. So you look at your question because it's not all points you need to get the value of the bending moment. You look at the question what you have to find, and look at the question and see where it is necessary for you to get the bending moment. So looking at this question, I have point A, point B, point C, and point D. So I think it's necessary for me to get the bending moment at those points. And from there, I draw my bending M/I diagram. So at a simply supported beam, the bending moment at the extreme is equals to 0. Therefore, MA is equals to 0 and MD equals to 0. So it's not left for us to calculate the bending moment at points B and C. So moment at B equals to, using the bending moment sign convention, this is the RA, is going in the clockwise direction, so it's going to give us a positive moment. And our RA we calculated already to be 4 kilonewtons. We have 4 multiplied by the perpendicular distance at 2 points B, which is 2. And we have this to be 8 kilonewtons. Then the bending moment at C will be equals to the RA multiplied by the perpendicular distance to C, which is 6 minus the 4 kilonewtons coming in anti-clockwise direction, and we have that to be 4 multiplied by 4. So this is 24 minus 16 equals to 8 meter. So we have gotten the bending moments at those points. So we now plot the diagram over AI. at point A, I have a 0 moment, then at point B, I have 8. I come to this point, 8 over EI. Then, the same thing at point C. Then we return back to this. This is the positive ending. In conjugate beam, we turn the supports of the original to the conjugates of it. And here we have a pinned support and a roller support. So the conjugates of those supports is still the same pinned and roller. So therefore, this will still maintain to be a pinned support, and this will also be maintained to be a roller support. Then the conjugate load or the vector, since it's a positive moment, it will point in a downward direction. So our loading will go in this way and will go in this way. The rotation is equal to the shear force at point A and also at point B. While the moment is the moment at point B on the conjugate beam or the conjugate beam. So what we're going to do now is we get the reactions at point A and point D if necessary. From there, we calculate the shear force and moment at the points we are required to calculate the rotation and deflection. When we get that, that should be equal to the same way we calculated for the support reaction at the beginning, the same way we calculate the reactions here also. So I'll have RA and RB. Then I'll take the summation of moments. This is point A. This is point B, point C, point D. So I'll take my moment at point A equals to 0. Okay. So this is the point. I will divide this into 3 shapes. This is the first shape, this is the second shape, and this becomes the third shape. The loading is in downward direction, then it's going to be taking a clockwise rotation to this point A, which is my reference point, where I'm taking my moment. So, for the first shape, which is the first triangle, I need to get the load intensity by calculating the area of the shape, then multiply by the centroid to get the moment. So, and there's a clockwise direction. I have a positive then multiply by the centroid. This is point A, so the centroid of this will be 2 thirds plus the second shape, which is a rectangle, multiplied by the centroid. The centroid will be 4 over 2 plus 2. So the centroid of this shape will be 4 divided by 2, which will give it plus the distance from A to the point B. When you add them together, that will give you the distance from the centroid to point A. Then we come to the third loading plus the area, which is half base by 2. Then we need to get the distance of this from the centroid to point A. So the centroid from this place, you will have something like this. Let's say this is the centroid. From this to this is given as base whatever. So plus, when I get this, I'll plus it from point C, the distance from point C to point A. That will give me the total distance from the centroid to point A. So I'll have 2/3 plus 6. Then this also, the RB, will go in anti-clockwise direction. Multiply by total distance, which is 8. You have plus 8 RB equals to 0. The summation of the vertical forces, the RA and RB is going upward, they take positive. Then the load intensities of the area we have in this diagram, which is the shape 1, shape 2, and shape 3, which is the area. When we evaluate this, we have this. Then, if you simplify all this, you arrive that your RA is equals to this. From what we calculated, we obtained that RA and RB is equals to this. So, for us to get the slope at A, we have to calculate the shear force at A. So, the shear force at A is equals to the reaction. So, therefore, theta A, or the slope at A, is equals to this. Then the slope at B will be equals to the shear force at point B. So, to calculate the shear force at B, you look at the RA is going up in the vertical direction, and the load intensity of the shape 1 is going down. So when we calculate the area of the shape 1, we get the load intensity minuses from the support reaction RA going up. And when you evaluate all this, you have that the rotation at B is equals to this. Then next, we calculate the deflection at B. And to get the deflection at B, you have to calculate the bending moment at this point. So, YB equals to 24, which is the RA multiplied by the perpendicular distance to point B, which is 2. Then the load intensity at the first shape, which is the area, multiplied by the centroid. The centroid of this shape to point B. When you simplify all this, you arrive that your deflection at point B is equal to this. Thank you.